Hey everyone, how you doing? So, I'm Clara and I'm back with another one of my science chats. And today I'm going to be talking to a friend of mine, Dr. Jessica Boland. So, Jessica is a material scientist, and even though we're both material scientists, she does quite different stuff to me. She's also a active campaigner for equity in STEM and diversity in STEM. She's a lecturer and a researcher in Manchester University, so my hometown. And yeah, just an all-round absolutely lovely person. And so let's meet Jessica and find out about her work, shall we? So, hi Jessica, welcome. Thank you so much for joining me, and it's absolute pleasure as always. So who are you? What do you do? What is your work and your research?
Okay, so I'm Jessie. Jessica, whatever you want. Jessica's a little bit like I'm in trouble, so usually referred to by Jessie. Yeah, I'm a lecturer at Manchester. I'm in the Department of Electrical Electronic Engineering, but also live in the Photon Science Institute. That's quite cool because it's a research institute that is interdisciplinary. So lots of different groups from physics, material science, electrical engineering, chemical engineering, etc. So my background is actually in physics. So I did an undergrad at Exeter. Still love going to Exeter. It's a beautiful campus. And also did a master's project there. That was in reflective plasmons, designer surface plasmons, and also reflective liquid crystal displays at a year in industry in Hewlett Packard in Bristol. So that was fun because also got to experience Bristol. And then went to do a PhD in physics again, but now at Oxford. So yet again, a different place. I'm exploring all of the UK. That's what I'm trying to do so far. And my research was mainly focused on terahertz spectroscopy of nanomaterials when I was there at Oxford. And then I did spend a bit of a year abroad. I went to Germany, learning more about terahertz, and now that's why I absolutely love terahertz. And before coming back to the UK and settling in Manchester and transitioning more to the engineering side. So now trying to use my physics knowledge, the terahertz characterization I've learned, but to something more applied, so device applications now. So that's kind of my research journey. Other interesting facts about me, I didn't always want to do physics or engineering. So I did want to be a professional ballerina, and there is embarrassing photos of me in tutus and stuff like that somewhere on Twitter. Please don't try and search for them though. Yeah, so wanted to do that as a career. Anyone that's ever met me knows that I'm vertically challenged and only 5 foot. So that was the end of my ballerina dreams. Interestingly, if you look at the corps de ballet, all of the group of beautiful ballerinas, they're very, very tall, a lot taller than 5 foot. So yeah, I had a backup plan, which originally wasn't science. It was things such as classics, Latin, languages. So I still love Latin poetry now. It's kind of my geeky pleasure on the side. Yeah, but then eventually decided I liked problem solving, which is what I guess took me into physics and engineering. I also happen to be hard of hearing or deaf with a little d. So I rely mainly on lip reading for communication. I'm starting to learn sign language now, which is a massive step for me, and I'm really enjoying it. It's making life a bit easier, especially with face masks right now. But that's another side of me. So you might see me promoting the use of British Sign Language quite a lot in science and STEM, and promoting accessibility.
That's awesome. We can definitely talk a lot more about that, and we will. It's interesting. I love that. I love your journey. It's interesting that so my first degree was electronic and electrical engineering, and of course you're now in a building in Manchester. I went from doing that in Manchester, but at Manchester Met, to being in Oxford in a materials, more physicsy group. Go figure. To kind of we passed.
We're the reverse, right, of each other.
Reverse.
There we go.
Yeah, it's I'm a little bit, sad to hear that they make you live in the photons group. I mean, did they not let you have a house outside of the department? Just
No, I just like stay there and sleep there all the time. So it's quite a nice, comfy office. But no, I do live away from the department. You'll be glad to know. Actually live in North Wales right now, so it's a bit of a commute, I know, but on the border between Wales, Saltney, and Chester. So I get the best of both worlds, and also the best of both lockdowns right now. So whether that's a positive or not, but yeah.
all right, I didn't realize that. I mean, Chester to Manchester, you're talking what, an hour if you're going in?
Yeah, it's about an hour commute. But yeah, it's because my partner works in North Wales, so he's an optics design engineer there as well. So it's the joys of a dual career. It's somewhere nice in the middle. But
Yeah, no, I had no idea. I didn't realize that's, like I say, it's quite a commute. I know because one of my cousins was in Chester and I was in Manchester, and you're
yeah,
further along. But like you say, at least you've got you're not too far from the North Wales Snowdonia region, I guess. You're a lot closer than. So, I miss
definitely.
those.
I can't wait to explore Snowdonia again. I haven't climbed it yet, so that's on the to-do list. So
There's I love especially Tryfan. I love Tryfan. It's such an amazing peak. It's just. It's got the two big rocks, because Tryfan's very triangular, and it's got the two rocks on the top, Adam and Eve, and I have jumped across them. It's funny because if it was at ground level, it's just like, it's not that big a jump. But when you're on top of a fairly triangular peak, it's like,
yeah, I'm not sure I'm that brave.
yeah, there's pictures of me doing it. It's great. Or everybody else in the group was like, no, a whole bunch of lads. No. What had happened, I climbed up on top of it, and it was a bit of a windy day as well. I climbed up on top, but there were so many people up there that once you climbed up, you had to do it, you know.
You can't back out.
Yeah. And it's funny because, like I say, you're jumping like a foot, and it's so pathetic, but because of where it's a whole different ball game.
Yeah.
Sorry, completely. I love Snowdonia. I absolutely adore Snowdonia.
You'll have to show me. You'll have to come, and then you can show me the ropes and stuff.
I think, gosh, I can't even remember when the last time. It must be 7 or 8 years. So yeah,
we'll have to do it then, definitely.
Yeah,
I might need encouragement to get to the top, so we do it together.
Yeah, oh, I'd love that. I would love that. But coming back to science. So you're talking about you were talking about the sort of techniques that you're using. So what is it you're actually looking at? You say you're looking at thin film materials, you're looking at different materials. How are you looking at them? What is it you're trying to see?
Yeah.
What sort of materials are you working with? I mean, what are you doing? What are your stuff?
Quite a lot of things, actually. So the materials can be quite varied. So I'm mainly looking at anything that we call low dimensional, so nanomaterials. So 2D materials, which could be graphene type materials, monolayers of materials such as transmission metal dicalcagenides. We're just going to call them TMDCs from now on. But those types of monolayer materials is one example, but also conventional materials that you might have, such as silicon in technologies, but trying to shrink them down to be nanomaterials. So often in something called a nanowire, which is quasi one-dimensional because the diameter can be on the order of maybe 100 nanometers, but they'll have lengths of 10 microns. And the reason we're going to this nanoscale is because the materials we have already, like silicon, are reaching fundamental limits. So we kind of reached a speed limit, if you like, for how fast devices can go, and also a limit on energy efficiency. So we need to start kind of looking at new ways to do that. And that's where quantum comes in. So when you go down to the nanoscale, there's lots of advantageous effects that you can use. So quantum effects that will make it more energy efficient. And these kinds of nanowires have already been shown that when you go smaller, you actually still have the same optoelectronic properties as those big bulk materials. So pretty cool. One of the important things for a device is the carrier mobility. So how fast your charge carriers are going. And that really will govern a device speed. So you want to have as high a carrier mobility as possible in a device. And these nanowires have the same mobility as that bulk material. So I'm quite interested in using them and exploiting them in a device. And they're cool because you can also fabricate them in very different ways. Yeah. So you can choose to dope them on nanoscale length scales as well. So change it from a charge carrier being an electron to a hole with different mobilities. And this is the basis of most solar cell devices, actually. You need to have a p-n junction, so a p-type with holes and an n-type with electrons. So you need that kind of flexibility, and these nanomaterials can offer that. So those are some examples. There's even a new material, which is even cooler, which is called a topological insulator. Now, these are really weird. That was the Brummie accent coming out there for weird. But the bulk of it is insulating, but their surface is almost perfectly conducting. So it's the same material, just one material, one kind of element, such as bismuth selenide or something. And, the middle of it behaves different to the surface, which is very bizarre. Yeah, weird, right? Yeah. But when you think of the surface as well, even those charge carriers at the surface behave differently. So they go close to the speed of light. So we've got rid of that speed limit I was talking about before. They also travel just in one direction. And if you put impurities in the way, they can't be backscattered. So you kind of put an artificial defect, it will just carry on going. So it's a bit like us being on an ice rink. You're going round in circles, but with less heat and less resistance. So it could be a solution to energy efficiency.
Wow.
So quite a lot of materials. I guess you should probably say how we look at them now, right?
that might be my next question. Yeah. What is it?
Yeah.
How are you measuring them? What is it you're measuring? And
Yeah. So these materials, you can't usually look at them with a conventional optical microscope because they're nanoscale. They're too small. Often if we want to measure that property, mobility, electronic properties, often you fabricate electrical contacts onto them. But again, if they're quite small, that's quite challenging to do. And also sometimes you can destroy them by doing that and alter their properties. So how we're looking at these materials is to use terahertz radiation. So you may have heard about terahertz possibly in the news because it's starting to be used in airport scanners now. But it's in between microwave and infrared. And its energy range encompasses the energies of those electrons that move, holes that move in our material, phonon modes, so how the material is vibrating, for example, also plasmons and magnons. So lots of properties happen to live in this terahertz range, which is awesome because then you can use it as a non-contact probe.
That's nice.
So yeah, nice. If I shine terahertz radiation at these nanomaterials, usually they will either absorb the terahertz radiation, so you'll kind of see a difference in signal. And it's that difference in signal that I'm measuring. And I can relate that back to the optoelectronic properties. So I can do some fun fitting and data analysis, and I can tell you the conductivity of your material, its photoconductivity, what that mobility is of any charge carriers, and also the lifetimes of those charge carriers, so how long they stay around for as well. So it's quite a powerful technique. And
Yeah.
don't damage your sample, and it's a lot easier than fabricating contacts onto something that's really, really small.
Yeah, I mean, I was making some solar materials and some semiconductors, and we had to cut them to the exact right size, and they're only a few hundred nanometers, and then you've got to put electrical stuff on them and and
Yeah.
do the whole measurement and then back. Yeah, so the fact that you can sort of measure them, that's really interesting. And so are they quite, I mean, obviously they're small wires, they're very small dimensions. Do you have lots of them? I don't, how does that work?
Yeah, that's a good question, because there's two types of technique. So normal far-field terahertz spectroscopy, you'll look at several nanowires. So we transfer nanowires onto a substrate, and they can be aligned in the same direction, they can be mismatched, they can lie on top of each other. So you can put several nanowires onto one substrate. And when you're looking at them just in the far field, so shining just a normal beam of terahertz radiation, you'll be effectively measuring an average conductivity. So the conductivity response of an ensemble of nanowires. And that can be tens of thousands of nanowires all in one go. So that's one way of doing it. Often there's problems with that though, because a lot of the devices are just one nanowire. So an example is a laser. You can make a laser out of a nanowire. Super cool. And there's actually other people at Manchester working on that. But that's just one single nanowire. So then you start asking the question of which is the best nanowire that I have measured? Which one do I actually want to pick? Often, sometimes for terahertz photodetectors, that's just one nanowire as well. So you want to look at one nanowire independently from that bulk ensemble as well. And also if you have any variations in your nanowire. So we were talking about different doping earlier, PN junctions. If you doped one end of your nanowire so that the charge carriers are mainly holes, and then the other end was doped with N-type doping so that you've got lots of electrons instead, you want to be able to see where that change in doping concentration is. So actually you also want to measure these properties on the order of like 30 nanometers or tens of nanometers. So even smaller resolution, if you like, or better resolution than one nanowire. And this is quite a new technique, and this is terahertz microscopy now. Yeah, and that's what we're trying to develop in my group now at Manchester. So
I mean, that's that's amazing. It's always interesting, and it just amazes me. I tend to look at materials that they might be a few nanometers in thickness, but they'll be 5 mil by 5 mil wide or something like that. I mean, you're literally, and that's tricky enough. And you're actually sort of taking down those, like you say, quasi one directional. It's like, just what the heck? That's tiny.
Yeah,
Don't drop it on the floor.
Exciting. Yeah, the spatial resolution of these techniques is really starting to push towards the nanometer now. And that's because we can also fabricate at that scale.
Yeah.
So we can actually dope on those length scales. So you need the characterization to kind of match up and also be able to look at those types of length scales, which is fun.
That's amazing. It's amazing. And are you manufacturing these materials, or are you getting them in to measure them?
Oh, I'm definitely not manufacturing them. That's where lovely collaborators come in. Yeah. So a lot of these materials come from different groups actually in the UK. And this is one of the beauties of research, how interdisciplinary it is. I am by no means an expert in materials growth or fabrication. So a lot of these materials are from renowned experts in their field. So one group is actually in EPFL in Switzerland. Anna Funkterberta's group, who make 3,5 nanowires, for example. There's also a group at ANU, Australia National University, Professor Chenapati Jagadish, who's another expert in 3.5 nanowires. So I get lovely samples from him as well. More closer to home, a lot of the topological insulator thin films are from a group in Leeds, so Edmund Linfield's group, and Torsten Hesjedal in Oxford. So you might know him, actually. He's a lovely guy.
I'm actually was speaking to him last week.
There you go. He gives me all my beautiful topological insulator nanowires. So
excellent. Haven't spoken to him for a long time, but yeah, we might be moving some equipment into his lab because COVID restrictions mean that they want to use it and we can't have more people in the lab. So it might be going to his lab.
Oh no.
Go figure. Oh, it's kind of good for me. We're limited on space, but
yeah. Oh, that would be good. Yeah, you have to say hi to him for me.
Yeah. No, that's amazing. That's great.
Yeah, loads. It's good because you get to visit different universities when you're talking to the collaborators, and also you get to learn quite a lot, because I've recently started working with Professor Huyin Liu from UCL, also an expert in nanowire growth. So it's quite nice to kind of meet all these new people, and they're doing fantastic work and experts in their own field. And then I don't have to worry about that side of it either, which is really nice. So yeah.
And I think that's one thing that's really important. It's something that we don't, it's the collaboration and the difference in expertise. Like, so I can make thin films. I don't know how to, I don't make nanowires, but I make nanoscale films. They're sort of different, and you've got the thing. And then when it comes to the measuring them, the sort of measurements that you're talking about, I have no idea about that. I mean, I have no idea, but that's where collaborations do come in, and that's why collaborations are really important, I think.
Definitely. You can't be an expert in everything. So, and I don't advise you ever should try. So I think it's definitely collaboration is the way to go. So
yeah. I mean, I've said this with other people in the past, but I love the groups where we have very different expertise within the group. I mean, Susie Speller, whose group, it's her group that I run, and she's great on the physics side of it, and I'd like to think I'm great on the thin film side of it, and we both know about the other, but in different ways, and just works really well together because we just look at things differently.
Yeah. You do need that range of ideas and opinions and just different outlooks.
Yeah.
Because everyone's got different experiences, definitely, in their lives as well, that will change how you look at things. And I think that's how good science is done, definitely.
Yeah, and especially when you're sort of talking about material science, it's such a collaborative thing. And there's, my last group in Switzerland were all chemists. I don't know about the chemistry, but I could get the equipment working and play with the plasma.
I've never done chemistry ever. I didn't do an A-level in chemistry. So I'm always like so happy when there's a chemist like collaborating, because I'm like, yes, someone that knows chemistry. So I can ask questions of.
It's just when they're dropping something, they'll make a statement about some principle that they learned about in the first year. And it's like, that's great, but I never did that. The same with physics. Yeah, I think we were talking about sort of quantum materials, and you mentioned quantum materials. Like, I'm trying to, as someone that didn't do physics, trying to get my head around that.
I got told a famous quote once that if you think you've understood quantum mechanics, you haven't actually studied it, because it's just so confusing, full stop, and no one understands it. So I think that was told me in like first year quantum mechanics course, probably by Professor Roy Sanders at Exeter. There's probably something he would say.
Yeah.
But definitely, it was encouraging to be like, we're never supposed to understand quantum. Brilliant. So
we can further the understanding, but we can't understand it. And that's what I love about science.
Yeah.
I've been working with people recently. I think that they were a little bit, they sort of, once they finally got the equipment working, sort of expected that the first thin film they make is going to be perfect. And I'm like, if the first thin film you make is perfect, I'm out of a job. Like,
I love it. You're like, please don't kick me out of a job.
Yeah, exactly. If we could just make them, why do we need scientists? So, yeah. So, yeah, like you say, keep me in a job. Yeah, exactly.
Yeah, but I think science is about failing and learning from that experience. So that's
Exactly.
experimentation. You're supposed to fail, and then it's not really failing. It's just a null answer, and then you move on from it.
So I was having, and I think, yeah, I was having a good discussion with Clara Nellis about this actually, because I was saying that the technology that I used during my PhD and postdocs was brand new. And so most of the time was just trying to get it to work. So many null answers. And yet we don't publish any of that.
Yeah.
And Clara was saying in practical physics, they do publish all the null answers because it helps everybody else move forward. And it's like, yeah, we should be doing that. Like, because that's important. I did all that work and then I speak to someone and it's like, oh yeah, we did that too.
You're like, we needed to know it didn't work. So,
yeah. I mean,
I do think null results are so important for that. Definitely. To know that you're going down the wrong alley and don't bother, it will be a waste of time. But also, sometimes it's worth going along the same route as somebody else as well, just to have that kind of reassurance that you've both seen the same thing sometimes. So that's experiments. I love it.
Yeah, I think it always depends, like, especially if you're like a research project, like a master's or a PhD, and you're working with other people that have got some expertise in the field, so you can learn off their knowledge and they'll be able to pass over. It's always difficult if you're the only person in the group doing it and starting from scratch. But yeah, no, I think I agree. I mean, failure helps us understand things so well, or at least. It helps us with our understanding. I mean, we do sort of change how we do things once we've got it wrong a few times. You melt a few bits of equipment and fry a few electrical devices, and hopefully you don't do that again.
I'm sure we've all done it. I've definitely fried some equipment. I'm not going to admit it on here though, just in case my old PhD supervisor's listening in. But we've definitely all fried equipment. So.
I keep on saying to everyone sort of in my lab, I'm like, look, you're going to break equipment and it might be expensive and I might not be happy about it, but it's going to happen. If you don't tell me and you just put it back in the cupboard or try and cover it up, then we're going to lose months and months trying to figure out what's going on. So it's going to happen.
Yeah,
just got to be honest about it.
I've definitely said that to my group now, that you're kind of like, this happens, stuff gets broken. So you're right, it's much worse not to say, and then you're kind of like, more time for everybody to fix it. So
exactly, you can just start looking into it. It's just so important. It's just good lab practice. Everyone's going to break stuff. It's just the way. That's a PhD.
Definitely. So
I used to work for a company that made equipment, and the way that they test things was turn it on and see what blew up. But of course, in industry, they've got the money to just replace the parts, right? Whereas in a university, if anything goes pop, you're like, no.
We definitely taught to be cautious, but that things still break, but just be cautious. But like, just see if it blows up or not.
I'm not saying that's the way to do it, but there you go. It's different when you've got more money, I think. We certainly don't want to be doing that. But so I mean, obviously you're working. So you're saying that you're measuring these things, you're saying in the terahertz range. I mean, what is it that you're using? Is this 5G? Are we going to be controlling people's brains?
Well, it could become 6G, definitely.
Wow.
So 5G is kind of on the top end of the microwave band. So actually, the next devices, 6G, are starting to push in the terahertz range. So the terahertz range goes from 100 gigahertz out to 10 terahertz. So it's quite long wavelength. And obviously you've heard gigahertz quite a lot for 5G. And I think it's about 50 gigahertz at the moment, 30 gigahertz, 50 gigahertz. So we're really not that far from starting to push in the terahertz range. So it's quite exciting, but it's also a challenge for that, because microwave and radio is very much electronics. You can deal with that as a lovely electronic engineer in the usual way, circuits, PCB boards, you're quite happy. Anything kind of above the terahertz range, you know, visible, UV, gamma, then you're starting to look at photonic techniques, so more light-based techniques. But terahertz is kind of just in between both electronics and photonics. And recently, like in the past decade, it's been quite challenging to get devices to work in that terahertz range. But now we're starting to have these terahertz sources that are starting to be able to be used in devices, which is quite exciting. So I would say a decade ago, the most common way of having terahertz radiation was to use a huge amplifier laser that's taller than me, use that laser pulse to excite a crystal, a nonlinear crystal, and then you get terahertz radiation. And that's still very much actually how it's done now. So I still have that amplifier laser that's bigger than me in the lab right now, and we're generating terahertz in that way. But obviously, if you want to have terahertz in a phone or any communication, that's not realistic. So trying to now do it electronically so that you can use circuits to generate that terahertz radiation. So that is a whole research field in itself. Which is quite fun. And actually, some of my research will try and answer those kind of questions. So trying to find those materials that you could use as a nice electronic device that will give you terahertz radiation out, also detect it and be able to switch it on and off. So, and then hopefully we'll have ultra fast 6G wireless communication. But there are some limitations, I should say. One of the things that you may not hear so much about with 6G or terahertz is terahertz actually has quite strong absorption lines from water vapor. Actually, if you wanted to use it for long range, it's a bit challenging because it would be absorbed by the water vapor in the air. So what you're most likely to see it used as is kind of instead of Bluetooth, so short range, but very quick wireless communication. So your long range is still done by 5G, but once it gets to your house, you might have the 6G terahertz to get it to your phone, for example.
So kind of like we transport electricity right now. You know, we ramp the voltage up and down depending on whether it's in the house or outside the house, right?
Yeah, exactly like that. So I think, yeah, definitely there'll be a lot of chat about that, I think, in the news coming forwards, because that's one of the key areas for terahertz research at the moment.
That's interesting. The fact that you've got these massive lasers in your lab as well. So just
I can send you a picture. I'll send one with me stuck next to it.
Yeah.
So.
Yeah. To be fair, we've got a laser in the lab, and it's probably about as tall as, well, it's as wide as I am tall, pretty much. And and yeah, when people are like, "So where's your laser?" I'm like, "No, that is the laser."
Yeah, I sometimes lie down by mine just to see how big it is. So
yeah.
Take a picture from the top, and it's quite amusing.
Yeah. So I mean, you're using quite a lot of lasers in the lab then? Is that what you're doing? You're basically sort of firing them at different samples and then trying to measure and see what's been absorbed or what's been
definitely absorbed. That. Yeah, so there's quite a lot of lasers because we look at photo exciting them. So with different wavelengths of light. So it really depends on the material. So sometimes we might photo excite them using infrared or visible or UV light. And it depends on what the band gap of the material is. Because we're always trying to photo excite and generate 3 charge carriers. And then those 3 charge carriers will absorb that terahertz radiation. So that's how we can then see the photoconductivity. So how are those charge carriers behaving? And we're detecting that using that terahertz signal. So there's quite a lot of lasers because you have one to excite terahertz in the first place, and then one to photo excite your sample. And if you want to do different wavelengths, it's a different laser usually for each wavelength. So I love playing with lasers. Just so many. So I'm always like, if anyone's like, oh, we're not using this laser, I'm always like, oh, interested, because yeah, they're really useful.
As the current laser safety officer for the department, it sounds like your lab. Well, I'm hopefully you know what you're doing.
Yeah, there's lots of risk assessments. Don't worry, lots of risk assessments, lots of laser safety goggles. Oh, yes. Yeah, lots of shields, all interlocked.
Yeah.
We're very well behaved.
Oh, you're good then. Yeah. You see, that's the thing. When people really know what they're doing with lasers, they got it sorted.
Yeah.
It's the people that just get one to try something.
No, we have to be really careful because they're all quite high power. So I always say that show a video of an exploding eyeball, because if you put one of our lasers on your eye, you wouldn't have an eye left.
Yep.
So it's quite high power, which is why you have to be quite careful and make sure you've got the safety in place. Definitely.
Yeah. Oh, yeah. No, I know. But I find it amazing, like you say, that you're not only that you can. It's fascinating enough that you can fabricate these nanoscale wires and actually use them and actually measure them. I mean, this is
it's really fun, because also when you look at the materials, how they're grown atom by atom.
Yeah. And
you can see that in a transmission electron microscope. And recently at Manchester, they've had a new system, which we're calling PNAME, which means that you can dope, so replace those atoms with a different atom on similar length scales, so 20 nanometer accuracy. That's tiny. So we really can like fabricate these materials now, atom by atom, change those atoms if you want, and then start to measure them on slightly not atomic scale yet. That's not my group, but there are groups out there that can do that. But yeah, nanometer length scales, and this is really what you need for nanotechnology. So
yeah, like I say, I mean, I used to use atomic layer deposition, so we were growing them atomic layer by atomic layer, but I was making bigger devices, I was making them bigger than that. It's just amazing. And the fact that we can use them, that we can actually, if you're making wires, it's because you've got a circuit. We're actually putting these into circuits. It's just amazing.
Yeah, it is super cool. Yeah, the atomic deposition has always fascinated me because it's basically Lego, but with atoms. It's like, yeah, amazing.
It's great. It's cool. It's just really slow for what I was doing. Depends how thick you need to film in the end of the day, but you can really concentrate. It's great. I don't know. It's just really interesting. And like I say, it's interesting for me that I think most people outside of what we do would sort of say, oh, we do the same thing. And we really don't. I mean, we have such different knowledge, but
But put us together, that's how it goes. Yeah.
Well, fingers crossed, as we were saying.
Yeah, fingers crossed.
There'll be something there. And always a good opportunity to visit Manchester as well.
Of course.
My hometown, my home city. It's how long have you been in Manchester? Have you been there a while?
Not that long. Time has flown. I think I arrived in 2018, so that's got to be 2 and a bit years now. But it doesn't feel that long because we moved to Chester, North Wales quite early on. So I'm still learning all the haunts of Manchester. So Deansgate was where I initially landed.
Yep.
And I love Deansgate. It's one of my favourite areas of Manchester. But I'm still kind of learning the little places, the best comedy clubs to go to, things like that. But I'm loving Manchester. It feels very like home because we were saying that earlier that I was originally from Wolverhampton or Birmingham way. So it's kind of a very similar vibe to where I grew up.
Really is.
Yeah, I feel quite at home. So I'm loving it so far.
Oh, that's cool. I think, I guess, because I think unless I didn't realize, unless I was oblivious, which is always possible, but I guess that's how long I've known you then, because I've always known you being in Manchester.
Yeah, it must have been how long we've known each other. Yeah, since I've come back. Yeah,
it seems like longer, but yeah, I guess so.
it does seem like longer, but yeah, it must have been.
And
I
before
probably
that,
didn't
you were
even
in
go on
Oxford.
till then. So
Pardon?
I was in Oxford, yeah, before. So I had 1 year in Germany, and then was in Oxford beforehand. But
So there's probably some crossover as well. But
there must have been. Yeah, there must have been. I was living in the condensed matter physics building, the Clarendon building, quite a lot. Yeah, I was at Jesus College. So, but we must have like seen each other around, but not realised at the time.
Yeah, I think I started looking at sort of diversity in STEM on a sort of more wider basis, really with, and people here have heard me talk about tigers a million times, but with the tigers, not that I didn't have interest in diversity on a wider scale, but just because it's so easy to get involved in sort of campaigning for the stuff that you know about. So in my case, LGBTI plus people in STEM, and it was with tigers that I really started to sort of expand out and make more contacts and learn people who are fighting for race equality and disability. And it's been really great to sort of learn a lot more. How long have you been, have you been campaigning or actively looking at sort of improving equity for a long time, or is it fairly recent?
Yeah, I would say that would say that my journey has changed. So definitely similar experience, that like joining Tigers in STEM really opened my eyes to all types of equity, diversity and inclusion. Because before that, I was quite passionate about campaigning for women in physics and also accessibility. But I would say that I was less educated on accessibility back then. So even when at Exeter and Oxford, it was very much, actively engaging in women in physics outreach, going into schools, talking about, picking physics, etc. And at Oxford, I helped out with the conference for undergraduate women in physics quite a few times.
Cool.
And recently went back on a panel, which was really nice to kind of be helping out on the committee and then actually go back and talk about it as a panel member. So that was really nice. So that type of work has been on my radar for a while. And
That's
also,
cool.
Yeah, I'd say also thought I wanted to go into teaching at one point and was quite passionate about different teaching methods, because being hard of hearing and deaf, trying to think about how I would adapt STEM teaching to make events more accessible. And that's when I started to really get educated more, not just about, my own hard of hearing experience, but, other types of access needs and issues and barriers in STEM for disabled researchers. And then it really came to a forefront when I joined Tigers in STEM, because that's when I think I started learning about intersectionality and how important it is. And also, not forgetting that I need to educate myself about race, for example. I knew nothing about that. And so being like, actually, I need to educate myself on that. Also on the LGBT side, meeting you has helped. I've learned lots of things. But yeah, like kind of educating myself on issues arising, barriers for LGBT researchers, and how also there is some overlap between all these different groups. So I would say that Tigers in STEM was definitely where I was like, okay, I'm going to start educating myself more, and have it kind of also gave me the confidence to campaign more for issues that I'm passionate about. So I would say that kind of spurred me on to be like, you need to campaign for these things, and gave me that confidence.
No, absolutely, and meeting other people that are campaigning, and what I like is good activism. You know, there's always, you'll hear a lot of people who complain about things, but they're not necessarily going about things in the right way. But when you start meeting other activists who are actually trying to improve things and be constructive, and it's like, this is wrong, but here's a solution, or here's a thought, and it's just a very different way of doing it. I know. I mean, I really started thinking about it when I first attended the LGBT seminar, and I realized that there was issues with LGBTI plus inclusion in STEM, which I only knew my story. I didn't realize the wider issue. And then, so that sort of helped me, and I met other people, and you see more what's going on. And then with Tigers, that sort of expanded it even further. And it's, because you don't always realize what the issues are. I mean, I think particularly if you're slightly older, further on in your career, you're probably used to just expecting things to suck. You know, I was on a panel the other day, and there was a woman who said, "Oh, it was great because I was finally treated as one of the lads." And I'm thinking, no, you shouldn't have to change who you are and, you know, try and fit in. You should be yourself. But I think, again, like, I knew that it's up for LGBTI plus people, but I didn't think there was anything I could do about it. And was it similar with you? And I mean, you obviously were active in the Women in Physics, but you know, as someone that is deaf, was that, you know, did you think that you could change things?
No, but I think it's also a bit complicated, because having to associate yourself as disabled is quite a personal thing anyway. So I didn't necessarily, you know, think of myself as disabled. I still don't, because I'm kind of like, you know, I'm not disabled. I don't have a problem. I can do things, etc. And this is where you come to the medical model and the social model. So the medical model says that, like, you are the problem and you need to be fixed. So your disability is a problem, and we're always going to treat it and solve it. And you need specific individual adjustments. But then the social model is actually, it's society and the environment that disables me, not my disability. And that is quite a difference. So it's like, if we change the environment to be more accessible, then I'm not disabled anymore. Like, and I think, so in terms of actually, you know, getting the confidence and thinking about that, I had to deal with that myself, about coming to terms with those two ideas and realizing that, you know, I was very much in the social model, that, you know, I don't feel disabled. I think it's an access need issue, that if we change environments to be inclusive for everyone, then, you know, I'm not disabled anymore. And that was definitely how I felt. But then having to accept that to get some of those access needs, you still have to register as disabled in Manchester and in different universities. It's not just Manchester. So that, you know, society is a little bit behind on that. So in order to actually get my access needs and access requirements, I had to kind of identify as disabled. But in terms of thinking about that journey, it actually made me go, okay, I need to now raise awareness of these two models and the social model, and also recognizing these different lived experiences. So that was kind of my approach to get there. Somebody else with a different disability might have a different lived experience. And that's really, really important. And that's the nothing about us without us, which I think I always say. And that goes for everybody with, you know, who's in a minority group or protected characteristic. I would even say everybody, full stop, that, you know, we all have these different lived experiences, and we should listen to that. So I think, you know, it was kind of a journey for me to think about that in my head, how I felt about it. Also owning that I'm hard of hearing. So, or when I was at undergrad, I was very much trying to hide it. It is a hidden disability. You probably wouldn't realise unless I told you, because of a lot of lip reading. There's no telltale signs. You know, if I go slow with my speech, you wouldn't notice anything. So it is a hidden disability. So it was easy for me at undergrad to kind of be in denial, feel shame, try and hide it. And then having that kind of wake-up call in PhD and very much now as a lecturer, and saying, actually, I'm going to be proud of this. Yes, I am deaf or hard of hearing, but actually we need to talk about accessibility and talk about these experiences and make change. So I definitely say it was quite a long journey. Don't know if that's answered your question, but
no, and in some ways it's interesting because completely different lives and completely different things going on. But I spent most of my time in denial and hiding, and I had to come to terms with myself, and so I understand that completely, actually. And it's interesting to hear that about something so different, and yet it's the exact same journey. And this is why it is important that we do work intersectionally and try and work together and try and figure these things out.
Yeah,
because there are a lot of similar paths. There's similar root causes. It's society is wrong. It's that lack of role models. It's that lack of being welcome. It's and because there's a lot of things that we do that we don't necessarily need to. I don't know. We're just going about it wrong. I see a lot of presentations and people have text which is really hard to read. It's really small. The colors aren't right. So now I try and have less data on a graph and I try and make the colors stronger. But I didn't realize that that was something that would help people who maybe were visually impaired. I didn't know that until I started looking into it. It's not like we're teaching people this. It's not like we're talking about this. We're only just starting to see people think about, like, well, do we have transcription? Does it need to be live transcription or BSL? Whatever it is. Have we started? So I say on one side, I feel like we're starting to look at these things more over the last few years. You might disagree.
I think there is more awareness now. I think so. I actually think that COVID has helped raise some awareness. So especially with working from home and remote working, that type of thing is things disabled researchers need and have been campaigning for a long time, for example. And I think it's starting to raise awareness that actually, while it will benefit disabled researchers who need flexible working, it also benefits everyone. If you do need to take time out because you don't have childcare, flexible working hours, for example, will really help with that too. So a lot of these little things are benefiting everyone, and that's always what I say about accessibility and all the things that I campaign for as well, that like women in physics as well. Lots of stuff that we make changes is helpful for everybody. I think as well, pronouns are a great example because it's inclusive of LGBTQ plus, right? But also, I mean, I don't see a reason that it doesn't benefit everybody. As soon as you come on a screen, you're like, okay, I know exactly what to use. So it's these changes I can't see a disadvantage to them basically because they benefit everybody. So I would say that we are starting to make progress, but we've still got a long way to go. So examples with the flexible working, it might be okay to take that time for childcare, but still not okay to take hospital appointments. So there is ways to go. I also think that the online learning has highlighted a lot of the things that you just said about the text having to be a certain size. Do we need subtitles or not? Should we have BSL interpretation? So I think those questions and those discussions are starting to happen, but they're still facing resistance. And from my own experience, I felt like I had to personally fight quite a lot to get subtitles used. And definitely I've tried to champion that within my own university and making sure all my own lectures, actually abide by the accessibility standards that I'm promoting. So definitely trying to say, okay, let's do this. But I don't think that once you address these issues and say, look, this is great, it benefits everyone, it's a small change, most people are receptive to that idea. So I think we are on an upwards trend and can make change, but we still need to keep fighting for it. And definitely still talk to those people with those lived experiences. And that's a message that I think we still need to try and get out. On the accessibility side, there is sometimes a risk of, people without that lived experience making decisions on your behalf. So, decisions associated with cost and what's considered the best practice in the field, but actually isn't used. And one example of that is the hearing loops now are infrared technology. So they used to be telecoil loops with a hearing aid, and now they're infrared. And you've probably seen them if you've gone to a theatre, because you have to wear something. And I always say that you look a bit like Iron Man, because it's like this big and you wear it and it's on your chest and you have to have it over your ears. Now, I don't like wearing that personally as a lecturer, because I go into a class and the students are immediately like, why are you wearing that? That looks hilarious. And then you have to own and say, actually, I'm deaf, which I don't mind doing, because they know that anyway, because I use sign language in lectures. But that's not necessarily a nice situation to put people in, and you have to give people that choice to use. Also, a lot of disabled students don't use that technology for similar reasons, that you don't want to sit there with something that's basically a badge saying I'm deaf. So I think there is more work to happen, more work that needs to happen, in terms of raising that awareness of the importance of lived experiences and that nothing about us without us, so that we get solutions that actually work for the people that need them. And I would say that that is a trend across all aspects of equality, diversity and inclusion, that we're starting to have these discussions, but we still need to focus on experiences, lived experiences, nothing about us without us, and how we get solutions that work.
Yeah.
No,
It's,
didn't I? But
no, it's good. And again, there's a lot of similarities that I'm seeing. It's interesting, because I was actually going to follow up and say, I can see that in some ways. So COVID has been bad for many people in many ways, but there's also been advantages. For instance, people with chronic illnesses can't necessarily leave the house to go to events, but if they're online, they can.
Yeah.
And also, people I know that I've put on events and people have been able to come from countries. I've had people talk to me at events who live in countries where it's illegal to be gay. And never heard any LGBTI plus people speak, and yet they could do that because it was online. And so you've got these amazing improvements, and I miss in-person events. As someone that does suffer from chronic fatigue as well, though, it's nice to not be traveling as much, because that makes it easier. So it sort of swings and roundabouts. It's interesting. Earlier you were talking about BSL, because with, and maybe this is a very specific thing, so people in general aren't so interested, but I am. I ran the LGBT seminar recently, and because we knew that it was international, but we wanted something. So it was, do we get live transcription or do we get signing? And because Live transcription in English is language dependent, it's English, but BSL is British Sign Language, it's language dependent. So which one do we use? And so we actually went with the live transcription as I feel that there's probably, I don't know, more people speak English. I don't know. I didn't know. It was a back and forth, and we were asking people, and we went with live transcription. I wonder if you've got any thoughts on that.
Yeah,
you don't have to have.
Yes, I do. Surprise, right? So actually, I would say that you should have both, if possible, at all times. And I know that often there's a cost implication for that. And that, I think, is a different issue of who should be funding those costs as well. So I would really, I'm advocating for, if universities hold events, that they should cover the costs of both live transcription and BSL. Similarly, conferences, I think, you charge conference registration fees, there should be a pot of money that is set aside for access needs. But I appreciate if you're doing, event that is ran mainly by volunteers, you might not have that funding available, so you have to do the best that you can. So the reason I always say both is that BSL is a different language to English, so it doesn't follow English grammar at all. It has its own grammar associated with it, and often users of BSL, that would be deaf users with a capital D, so whose first language is BSL. So you have to assume that they might not actually know English. So although, some of the signs are similar, it's equivalent to a French person trying to understand an English lecture without any English knowledge. So that's why I say both interpretations. Often as well, there's a lag sometimes with live transcription. So BSL is often faster, so you can keep up to date a lot more. But live transcription is also important. And I'm quite vocal about the difference between having a captioner, so someone that sat there typing live, to the closed captions that you might have on Zoom or Teams. So live transcription is also really important because often, closed captions, I'm sure we've all had those moments where we're kind of laughing at the subtitles when they've got something wrong, especially with technical vocab. But if you are trying to listen to a meeting and you're relying on those subtitles, you just can't engage in that meeting. And also, you're probably second guessing the subtitles. So I do this a lot. I use subtitles wherever I can, especially in big meetings where I can't lip read. And often I'm like, oh, it's trying to say the element molybdenum. It said moly, big dom, or something like that. And you have to then guess, and it's extra workload for your brain. So you're working overtime, if you like. Similar to the Zoomitis that everybody was talking about. That's how you would feel. So live transcriptions are much better than closed captioning. And I would say that should always be included, definitely. And BSL, if possible, there should be hopefully enough funds to have both because you're engaging both users. Also, if you're hosting events, don't be afraid to ask people what their access needs are, so that you can plan for that. So it might be that if it's not an event for the whole general public, it might be that you don't actually have any users that need to use BSL, and you're not opening it out to the public, so you don't need to worry about that, and you can then only just have live transcription. If it's for the public, then you have to assume that you're going to have a broad range of access needs. But if you are dealing with that, just ask people, and I'm pretty sure they will tell you. So, yeah.
Hopefully so. Yeah, I mean, we did have that where we also asked as well because everyone had to register. So, and like I say, it's difficult. It's difficult to know. And the one thing, another consideration was that And this is something that I've had a number of conversations about recently, that there's a lot of scientific terminology which doesn't have a BSL sign.
Yes, definitely. And this is something that I realized very recently, because my hearing started to get worse. And when I was in Germany, I had to have quite a big operation to recover the hearing and not lose it completely. So it was a kind of wake-up call for me to actually start learning BSL. So I didn't have the opportunity as a child for several reasons, partly just medical doctors, diagnosis issues, and also it was expensive. Couldn't afford it as an undergrad, couldn't afford it as a PhD student. Now I'm in a position where I can afford to take lessons, so that's great. And really have started to find it much easier, especially for situations like the lab. Also, face masks are an absolute nightmare for me. So I can't communicate now with face masks, lip readings out.
Yeah.
And that's where sign language is starting to kind of replace that. I would say that face masks are still tricky for sign language because there's a lot of facial expressions and body language and communication. But there are situations that start to become more difficult where I can't use lip reading anymore. And that's where sign language is really helping. But I noticed when I was learning that if I did want to use it in the lab, there wasn't that many signs, and immediately was like, there wasn't a sign for terahertz radiation. So I was like, oh, I can never talk about my research. What am I going to do? And then I found the Scottish Sensory Centre app, which is fantastic. I recommend everybody download it. It's from the Play Store. You can just type BSL education, and that is videos and definitions in BSL of signs that are related to science and technical vocab. So physics.
Is that the Glasgow group?
Yeah, the Glasgow group. Yeah, they're really good. And a lot of the signs that I was doing at Twitter come from that app. Other groups as well. So from my deaf centre as well, starting to learn different terms. But it's quite difficult because there's different regional signs. Numbers are completely different all over. So when I was a child, I learned basic BSL at school. So very level 1 numbers, colours, and obviously learned Birmingham signs, completely different to Manchester signs and Exeter and Bristol. So for the science vocab, we need a glossary or a dictionary that we can all start to learn these signs, and they're consistent across the UK. And it's important for ensuring that, deaf students want to take STEM and stay in STEM. So
yeah, I was talking about the Glasgow group in a meeting because I saw them do a talk end of last year on this very topic, which is the only reason I know. I just and the Royal Society are looking at funding some more terminology, basically. And I said, well, don't start from scratch. There's a group already working on this. And so it's really great that actually what we're seeing is that there's a few groups that are looking at doing this. And so if we can hook them up so that they're not all developing their own terminology, and even better if we can also in some way try and sort of collate that with what's going on in America and other countries, so that again we're not sort of, when we're naming elements, we're trying to do that globally now. We don't want to do them in each language. We want to try and do it globally. So let's do that with terminology in this as well. But yeah, it's like I say, I had a conversation about it just last week, and it was something that I happened to have seen a talk about 5 months ago. Before that, I didn't consider it. I didn't realize, and I should have done, because I just used the example of different languages. My ex-girlfriend is Polish, and she worked with other microbiologists who were Polish, and they'd be talking away and then English words, English scientific words, because it's trying to make these words global. So I should have thought about it, but I'd never put two and two together.
I think it'd be really exciting to keep putting that vocab in the BSL. And like, my dream is that, there will be lecturers who are lecturing purely in BSL in engineering. So that's what I hope to do, because I'm learning for myself, but also it would be great to be able to do a lecture on electronic materials purely in BSL so that people can access it as well. And that's what I think we need.
I do. I'll be honest, I love, because you do things on Twitter where you show different words, show how to do different words. And I'd actually learned a few of them, and then I remember them for 6 months, and then they slip out of my mind. I'm terrible. And it's one of those things that, I'm not great with languages, and I see this as another language, and it's the same with music. I've got my guitar behind me and I struggle. It's just trying to remember. So we all have brains that work in different ways, but it doesn't mean that we can't try. And
it's going really interesting actually, because I started using some of the engineering signs from the app in actual lectures this term remotely, and it was really nice to see it actually reinforce some of the concepts, because some of the signs literally look like what you're trying to explain, and that is one of the beauties of BSL, how visual it is. So I guess I can give an example, but like conductor is like the current flowing over a line that's a wire. So you're like, it makes sense logically. And it was another way of teaching students. So even though there was non-deaf students in the class, they still found it useful and, as reinforcing, as a teaching element as well. So that was a nice surprise, and another example of how these access needs can benefit everybody in a surprising way sometimes. But
well, this is it, and it's never one group that benefit from things. There's always more, like you say. And I'm thinking of like recently some journals have started allowing you to change names, and that's really great for trans people, but it's also good for people who are, for some reason or other need to change their name for security reasons, or because they want to because of marriage or stuff like that. It's not just one group that benefits. There's more. I mean, if we had single stall bathrooms, all of them could be more accessible, all of them. At the moment, you have to have special provisions on every other floor or something, and it's like, well, why are we doing this? And now I was thinking about this morning, because with COVID, we've got this big old bathroom, loads of stalls, but you can only have one person in the entire space. Well, if they were single use,
loads of these examples, definitely.
So if we can, it benefits everyone.
Yes, definitely. Keep campaigning. That's the message. So
absolutely.
There's been a really good phrase which Hamid said to me the other day. We were talking about Hamid, who's wonderful.
I met him last week.
He's the chair of the National Association for Disabled Staff Networks. And he's at Manchester, and he's set up our disabled staff network there. So he's super awesome and really hot on accessibility. And he said a phrase that really struck with me, which is not disabled yet, and kind of trying to explain accessibility in that terms, that who knows, you might lose your hearing when you're older, that all of these things will benefit you, if not right now, could be at some point, and getting people to think about what if you were in this situation, what would you like? And that's always struck with me, this kind of benefiting more people than you imagine, and also like trying to understand that lived experience as well, then I think about us without us.
Absolutely. You just don't know what people are going through, or those that, like you say, those hidden disabilities, that people like myself who are LGBT and not out, and the different people from mixed backgrounds and things like that. There's so many things that you just don't know. You help more people than you realize. Often I don't know if you watch the cartoon Adventure Time, but they had they did a special recently, and they had something really similar that, one person was, they were talking about, one person was the outcast, and because they had a crack, and then once they're like, actually, this is a good thing, everyone's like, oh, so have I, so have I, so have I. It's great that there's cartoons that can sometimes just sort of demonstrate these so simply, but you have no idea. And this idea that you just said, not disabled yet, is really, you have no idea. I'm getting older.
Yeah, it kind of struck with me that was like, oh, that's an interesting way of framing it.
Yeah, it really is. It really is. Oh, and what a lovely individual as well. Like I say, it was the first time I met him last week. So
he's awesome. So loads of pearls of wisdom. I've learned loads from him.
So. I'll definitely be, for those listening, I'll definitely be trying to get him in for a later
please.
interview.
He will be very interesting, I think, to talk to, definitely.
Well, with that, is there anything, I mean, we covered quite a lot and I've kept you much longer than I thought I was going to, but is there anything that you feel like that you should mention, that you should highlight, or do you think we've covered a lot of ground?
I think we've covered quite a lot of ground. So, just that, I guess I was like, for all your listeners maybe, but like if they did want to ask any questions, then they can feel free to email me. I'm not sure I'll always have the answers, but if they did just want to chat about any of the topics we've discussed, and my love of terahertz even, then they can just email anytime.
That's amazing. Well, what I'll do is I will get the details that you want to share and put them in the links, whether it's the podcast or YouTube. They will be below. So just make sure it's the ones you want to share. And and with that,
check them.
Thank you so much for the chat.
Thank
I could talk for hours, obviously, but
it's been really, really fun. So thanks. I appreciate it.
Oh, thank you.
Yeah.
So that's Jessie. It was an absolute pleasure. As usual with these chats, I could have gone on forever, if I'm perfectly honest. It was really nice to catch up, especially as I've not actually been able to meet in person for a long time with a lot of these people. But yeah, hopefully that was an interesting overview of the work that she's doing and the work that she's into, and learn a little bit about Jessie. And I know I actually learned a few things today as well. So amazing. I'll put the links below on the YouTube video for Jessie's socials. And in the podcast, they'll be in the description, hopefully. And with that, like, subscribe, tell your friends that we're here. And with that, I'll see you again soon. Until next time, bye.